Expressing solution concentration. There are qualitative descriptions of solution concentration, dilute and concentrated. And these are just relative terms, okay? It's, what are you comparing it to? It's like a rich person and a poor person. Well, it depends on who you compare them to. But a dilute solution will have relatively small quantities of solute, and a concentrated will have relatively large quantities of solute. And then there are numerous quantitative measures. So here's a table from your textbook summarizing these. We have already talked about molarity because we've used it a lot. But there are other units as well. There's molality, mole fraction, mole percent, and then all the parts by. You can have parts by mass as a percent, a parts per million, parts per billion, or a trillion, or gazillion, or whatever. And then you can also do parts by volume. And then there's also mass volume parts. So this is just a summary. So molarity, we've talked about before, but we'll just go over it again. Molarity is the amount of solute in moles divided by the volume of the entire solution in liters. And those units are important. It has to be moles per liter. Now, one of the drawbacks of molarity is that it changes slightly with temperature, because the volume of a liquid changes slightly with temperature. And so the molarity will change with temperature. And so even though chemists really, really like molarity because we deal with moles and volume is so easy to measure, it is not appropriate in all situations. And that's part of why we have all these other different things. And here's just a picture illustration of how you would make a standard solution. So that was covered more extensively in section 4.4. Molality is similar to molarity, but it is not the same. So this is, again, the amount of solute in moles. But now we're looking at the mass of the solvent, not the entire solution, just the solvent. And it's the mass of it in kilograms. The advantage of molality is that it does not change with temperature. Okay? Chemists don't use it very much, but it's very useful when you're dealing with something where the temperature varies a lot. So really important, kilograms of solvent, not solution. That's the most common mistake. Then parts by mass and parts by volume. So parts by mass looks at the ratio of mass of solute to mass of solution. So it's the mass of the solute divided by the mass of the solution, and then times some multiplication factor. And that factor is indicated in the name. Percent literally means per 100. So percent is the mass of the solute divided by the mass of the solution times 100. We're familiar with that. And then percentage can be written as a very convenient conversion factor. 14% by mass means that the solution has 14 grams of solute per 100 grams of solution. It's how many parts per 100 parts. Parts per million is how many parts per million parts. So if you're trying to calculate that, you'll take the mass of the solute divided by the mass of the solution, and you multiply by 1 million. Parts per billion is solute over solution again, times a billion. And we can express these as conversion factors. 15 parts per billion by mass means you've got 15 grams of solute in a billion grams of solution. Parts per billion is a very small concentration unit, but it's useful in things like water testing. If you ever look at the water report that comes from the municipal water source, or your water plant, a lot of things are listed in part per million or even part per billion because there's very tiny quantities of them in the tap water. Any questions? Parts by volume is the same pattern. You can have percent, parts per million, parts per billion, but now we're looking at volume of solute divided by volume of solution times whatever the appropriate multiplication factor is. So if we say that a solution is 22% ethanol by volume, that means it has 22 milliliters of ethanol per 100 milliliters of solution. If the solution is aqueous, the parts per million or parts per billion by mass and volume will probably be similar, but they're not going to be exactly the same because the density of the solute is different. So using these things, these parts by mass, for example, in calculations, we need to know how to do this. So what mass of sucrose, and they give us the formula there, in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass. And it says assume a density of 1.04 grams per milliliter. So there's a bunch of numbers in there, and we need to kind of pick this out. So first of all, what are we trying to find? The mass of sucrose. What mass of sucrose? So we're trying to find out how many grams of sucrose. And then there's these numbers. We've got this milliliters. The 12 ounces here in parentheses is really to help you just have a reference. We're talking about a 12-ounce can of soda here. So we've got 355 milliliters. Is that the solution or the solute or the solvent? That's the whole solution. And it can be helpful to identify what these things are talking about. And then 11.5% sucrose. Well, what does that mean?
That's the solvent.
Sucrose is the solute. What do you think the solvent is? Water. But 11.5% means what?
11.5 grams for every 100 grams.
Yeah, so 11.5 grams of sucrose per 100 grams of what? Of the solution. Molality is the only one where we talk about the solvent. All the rest of them are talking about the whole solution. And then they give us a density. 1.04. Now that's pretty messy. 1.04 grams per milliliter. Most problems, you should at least see, could I do this using dimensional analysis? Sometimes you'll look into it and you're like, nah, I need an equation somewhere. But try dimensional analysis first. So if we're looking at this in terms of dimensional analysis, we have to figure out which of these numbers to start with, right? What did I tell you about choosing a number to start with? Look at the units. So this one just has a single unit, milliliters. Could this be a conversion factor? No. It's just a volume. We've got 355 milliliters of this soft drink. I can't convert that to anything. Could this be a conversion factor? Yeah, this relates grams of sucrose to grams of solution. Could this one be a conversion factor? Yeah, grams per milliliter. Any unit that has per could be a conversion factor. Okay? So that tells me I'm probably going to start with this one. So I'm starting with this. And then I'm trying to get to grams of sucrose. So I have to figure out the path. It's kind of a review of dimensional analysis here. Yeah, I can use this density because the density, is that referring to the density of the sucrose or of the soft drink? It's the whole thing, the soft drink. So that's grams of solution per milliliters of solution. So this density would allow me to convert from milliliters of solution to grams of solution. To grams of solution. Chemists get tired of writing the ocean part, and so we just put a parenthesis there, apostrophe, sorry. So from grams of solution, well, this term has grams of solution in it and grams of sucrose. And so this would allow me to convert from grams of solution to grams of sucrose. Any questions? Some of you are still not very good at this. And now is the time to ask questions and figure it out. So I've got my path. Now I'm going to just follow the pattern. So 355 milliliters of solution. My path has 2 arrows. That means I'm going to have 2 conversion factors. Milliliters of solution to grams of solution. And then on the next one, I've got grams of sucrose. That's milliliters of solution to grams of solution to grams of sucrose. And then I want units to cancel out, so I take milliliters of solution and I write it down here. So those are going to cancel out. And then I have grams of solution down here, so those can cancel out. Got all the units worked out. Now I put the numbers in. It's really, really important to put the units in there, okay? And when you have 2 different things, like, here we have grams of solution and we have grams of sucrose, you need to label grams of what? Otherwise you can get things backwards and then you get the answer wrong. So I've got this one, 11.5 grams of sucrose. So that one goes over here. Sucrose is on top. So the 11.5 goes with grams of sucrose and 100 grams goes with the solution. And then I have this density, 1.04 grams of solution. Well, that also happens to be on top, 1.04. This is grams per how many milliliters? 1. Now, chemists don't like to write the number 1, so we often leave it out. So now we just do the math. 355 times 1.04 times 11.5 divided by 100. How many significant figures should my answer have? 3. So 42.5 grams of sucrose. That's a lot of sugar. No, it's sucrose. Sucrose is sugar. Sucrose is table sugar.
But some drinks use the US.
Some of them, yeah, some of them have high fructose corn syrup.
So I've actually, I figured this out before, and I actually, to give like an idea of how much that is, it's exactly a shot glass of sugar.
A shot glass of sugar.
I measured it, I weighed it out, exactly a shot glass.
So that's kind of disgusting, huh? Think of it, a shot glass of sugar in your can of soda.
Wait, is that including the shot glass?
Yummy.
Just making sure.
I'd say it.
Yeah, no alcohol in there either.
No.
So, just kind of, it's hard to know, well, how big is a gram of anything? A lot of solids have similar densities. A gram is about the size of a green pea. So, it's 42 green peas. You could see that fitting in a shot glass because they wouldn't have to have all the packing issues with the open space in between. So, any questions? There are all kinds of problems that can be asked. And if you understand how to manipulate the units, it's just a puzzle. If you don't understand how to do the units, it's pretty hopeless. Because there's no, okay, well, here's 5 different types of problems you need to know how to do. And you just memorized how to do them. That's not going to work. You have to be able to think about it and figure it out. But you learn how to do this, and you can solve all kinds of real-life problems, too. And so it's a really good skill to have. Another unit, 2 other units, mole fraction and mole percent. And we've used these a little bit already. Mole fraction is symbolized by chi. So chi solute, this expresses the concentration as moles of solute divided by the total amount of solute and solvent in moles. So amount of solute in moles divided by, it's essentially moles of solution, but you have to calculate those separately. It's the total number of moles of solute molecules and solvent molecules. And so it's often expressed this way, where N represents amount in moles. Mole percent is just the mole fraction times 100. So it's just making it into a percentage. So there's mole fraction and mole percent. Do you remember where we saw mole fraction?
Chapter 5.
When we were talking about gases, right, in chapter 5. So we were looking at partial pressures and we looked at the mole fraction. And the mole fraction is related to the fractional pressure for a mixture of gases. Okay, so this is a long question. So we're talking about one solution, but we're going to calculate the concentration in all these different ways. The solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. And I'm missing a period there. Calculate the concentration of the solution in each unit. So it looks like we're talking about that can of soda again, right? But this one has a little bit more sugar than the one we were looking at before. Okay, so if we want molarity, calculate the molarity. Well, the first thing to do is just ask yourself, well, what does molarity mean? Molarity equals moles over liters. Moles of solute divided by liters of solution. Are either of those numbers directly given? Not quite, but this is the volume of the solution in milliliters, right? So we can convert that to liters. So that's going to be 355 liters, 0.355 liters. How do we find the moles? We need the molar mass of sucrose, don't we? So we've got 50.4 grams of sucrose. And we're going to use the molar mass. So we have grams on the bottom and moles on the top. And we have to calculate that. But they gave us the chemical formula. So we have 12 carbons times 12.01 plus 22 hydrogens times 1.008 plus 11 oxygens times 16. And so this gives me 342.3 grams. So 1 mole of sucrose weighs 342.3 grams. So I've got 50.4 grams, and I divide by 342.3. And that equals 0.147. There's my 3 sig figs. And I'm going to carry 2 extras to 4 moles of sucrose. So then I put that into my equation, 0.14723 moles. 0.14723 divided by 0.355. And so this is 0.415 moles per liter. Any questions? That one should be pretty easy. Okay, mole fraction. What is mole fraction? moles of solute divided by, yeah, moles of solute plus moles of solution. Because you can't calculate the moles of the solution. I mean, the way you do it is you take the moles of solute and you add the moles of solution. So we might as well just say that. Well, we just calculated the moles of solute, right? 0.14723 moles. And then in the bottom, we've got that number again, plus the moles of water, the other part of the solution. How are we going to figure that out? We're given the mass of water. So the mass of water, 0.332 kilograms, 0.332. Instead of kilo, I'm going to write what it means, 10 to the third. That many grams of water. And then we need the molar mass to convert that to moles. 18.02 grams per mole. 0.332 times 10 to the third divided by 18.02. And that should also have 3 significant figures, so I'm going to keep 3 and a couple extras, so 18.424 moles. Seems coincidentally close to the molar mass, but did anybody else get that? Okay. Sometimes you just have coincidences with numbers. So that goes in here, 18.424 moles. And that has 3 sig figs. So, just for clarity with significant figures, I'm going to write down the intermediate value in the bottom. So the top was 14723 moles. And in the bottom, we've got the 18.424 plus the 0.14723. And so that comes out to 18.57123 moles. But where is the last significant digit in that sum? This has the uncertain digit in the 3rd decimal place. This has it in the the 1st decimal place. So this has uncertainty in the 1st decimal place. It ended up still having 3 sig figs. But you can't know that without looking at the actual value in there. So 0.14723 divided by 18.57123. And so this is going to be 0.00793. What's the unit on that? Moles cancel. There's no unit. Mole fraction has no unit. If we wanted the mole percent, oh look, letter D wants mole percent. How do we make this into the mole percent? Times 100. So point.
that was the preview?
Pardon me?
That was the preview?
Kind of. So we end up with 0.793. Now it has a unit, percent. Any questions? Yes?
So that part right there, when you wrote it down, it should be solvent, right, on the, where you have solute, and solution? Because that threw me off a little bit.
Oh, yes. Thank you. I was not wanting to write out that whole word, I think. Yeah, this shouldn't be solution. Solvent. Well, when we look at the mole fraction, it looks very dilute, doesn't it? But when you think about 50 grams of sugar, that's more than the shot glass of sugar in the 12-ounce can of soda. That's actually a lot of sugar. The reason the mole fraction is so small, even the mole percent looks small, is because the molar mass of sugar is 342 grams. And the molar mass of water is only 18. So when you're comparing numbers of particles, there's not that many. But when you compare masses, it's very different. Okay, how about molality? What does molality mean? Yeah, so that's moles of solute per kilogram solvent. Well, we already calculated the moles of solute. 14724. Squeezing myself out here. I should have chosen a different color. And they gave us the kilograms of solvent. So I've got 0.14724 divided by 0.332. So 0.443 moles per kilogram. Usually how that's written, though, is, and this I think is just one of the stupidest things, it's a lowercase m. It's an italicized lowercase m. Yeah, good luck telling that from m for meter. But anyway, one of the many reasons I don't like molality. But I have to teach you about it. So there it is, 0.443 molal, not molar, molal. Pardon me?
Is there such thing as a kilomole?
You could have kilomolals, yeah. It would look like kilometers, yes.
No.
That's just, yeah, we're just, joking around being silly. Okay, percent by mass. What does that mean? Yeah, grams of solute divided by grams of solution. And it's percent, so times 100. Well, what's the mass of the solute? Oh, it gave it to us, 50.4 grams. What's the mass of the solution?
332 grams.
No. 332 grams is the mass of the solvent. You have to add the mass of the solute. Okay, this is one of my favorite trick questions. So you've got 332 grams for the water plus the 50.4 grams for the solute. So 50.4 grams. It's so simple and so easy, and yet there are so many places that you can screw it up. Yeah. That's why it's helpful to write everything out. When you write it all out, then you can see what you're doing. Now, I forgot the times 100%, times 100 there. Okay, so in the denominator, we still have 3 sig figs. 50.4 divided by 382.4 times 100. Sometimes students forget to multiply by 100, and that's always just very tragic. And the unit here is percent. Because what happens to the grams? They cancel out.
Is that like the same as like on tequila or vodka, and they give you the alcohol content?
Yes, when they give you an alcohol content in a beverage, it is generally I think it's probably a volume percent,
Oh, okay.
but it could be a mass percent. They're going to be similar, but yeah. And proof is actually the percent times 2. So 200 proof is pure alcohol. So if it's 100 proof, that means it's 50% alcohol.
And you said there's a difference between molality and molarity. Now, we would choose molality if the temperature is very.
Yeah, molality would be used when you're dealing with situations where temperature changes.
And is that like in a closed container where like the solution can expand?
You know, off the top of my head, I'm not real familiar with any situation in which molality is useful.
Okay.
I really think it's stupid, but there it is. Now, the percentages in parts per million, percentages are used a lot in medicine, and I think the reason is they're very easy to make the solutions. If you want a 75% sugar solution, well, you weigh out 75 grams of sugar and you add water until it weighs 100 grams. And so there's a lot less measuring. The reason chemists like molarity so much is we're always looking at chemical equations, and it's easier to find the number of moles of something that you're dealing with. And so which unit you use depends on what sort of a thing you're doing with it. So they're all useful in different situations, right? And as a scientist, it's important to be familiar with them and know how to convert between them. Okay, here's another one. Seems a little redundant, but let's do it anyway. What's the molarity of a 10.5% by mass glucose solution? Now, this is glucose, not sucrose. The density of the solution is 1.03 grams per milliliter. Again, I would start out by asking myself, well, what do I need for molarity? I need moles over liters. So molarity equals moles of solute, in this case glucose, per liter of solution. This is a situation, you could solve this using dimensional analysis, but it might be more straightforward to be looking at this equation and just finding these two pieces and dividing. So I have this solution. Well, it's 10.5% by mass. So 10.5% means 10.5 grams of glucose per 100 grams of solution. And we're trying to find the molarity, and they're also giving us the density. So the density is 1.03 grams per milliliter. And that's grams of solution per milliliter of solution. They gave us two numbers. They both have per units in them. What do we start with? Yeah, so we could choose an amount of solution. This is not one where they're saying it's a can of soda or it's this much or that much. They're just giving us a solution. They're giving us one concentration, asking for a different concentration. So we could just pick an amount that's convenient. We could say, well, we're going to pretend we have 100 grams because that seems like it would be easy. Or we could say, well, really, this percent is the concentration, and I'm wanting to change this percent into molarity. And so I could change the grams of glucose into moles of glucose. And then I need to change grams of solution into liters of solution. That would be the dimensional analysis approach. So which one do you want to do? Pick an amount or dimensional analysis? Okay, we'll do dimensional analysis. This is like back at the beginning of the semester where we had 55 miles per hour, convert that to meters per second. It's the same idea. So I'm going to take this starting point, 10.5 grams of glucose per 100 grams of solution. I'm going to have a factor where I convert grams of glucose to moles of glucose. And then I need to convert grams of solution to liters of solution. Well, depending on how comfortable you are with metric units, you might want to go through milliliters in there. So we're starting with the 10.5 grams of glucose per 100 grams of solution. I like to do the thing on top first. So I want grams of glucose in the bottom, and I want moles of glucose in the top. So that grams of glucose cancels out, and now I've got moles of glucose per 100 grams of solution. That's not so useful, but it's a step in the right direction. That's this one right here. Now I want to convert grams of solution that I've got in the bottom to milliliters of solution, and then to liters of solution. So when you're converting the bottom unit, then what you're trying to cancel, this grams per solution, I need to have that on the top. Grams of solution, because that's going to cancel out, right? And the thing I'm trying to go to stays in the bottom, grams of solution to milliliters of solution. And then I want liters of solution. So I need milliliters up here. So those cancel out. Any questions? Several of you look rather concerned. If this gets confusing, then convert each of them separately and put them back together. That's another way to do it. So milliliters per liter, milli means 10 to the minus 3. So on the bottom here, instead of writing milli, I'm going to write what milli means. And grams per milliliter, that's the density that was given. 1.03 grams per 1 milliliter. And then I need the molar mass of glucose. So 6 times 12.01. 181?
No,
180.1? Okay, so we'll call it 0.2. 180.2 grams. And that's 1 mole. So now just take care of the numbers. So I have 10.5 divided by 100, divided by 180.2, times 1.03, divided by 1 times 10 to the minus third. So this comes out to be 0.6. I should have 3 sig figs, 600 moles per liter, which is 0.600 capital M. Any questions?